Great, so this is the problem that we're going to tackle. So let's see. Okay, so first off, we spoke about the one finite element that we're going to put down. You have put down the psi domain -101. Okay, and then here I've associated the x coordinates to each of those nodes. So this x coordinate x1, or with node 1, the x coordinate is x0 with node 2. X coordinate is x1, and with node 3, x coordinate is 0.5. And here are the coordinates x1, here the node, the displacements that we're going to, unknown displacements that we're going to solve for, q1, q2, q3, unknown weighting functions, coefficients, w1, w2, and w3. Okay, so what we're going to do is we're going to first look at the weak form and say this is the problem that we're going to tackle. Okay. And all that's different now with the finite element method with what we've done before is we're going to follow exactly the same steps. The only thing that's different is the form for W and the form for U that we're assuming is what we looked at yesterday. Using the shape functions and using these unknowns Q1, Q2, Q3 that are nicely uncoupled. They have nice interpretation, so we know exactly what they mean and how to work with them. Okay, so that's first thing. So that's where we're going to go. Okay. The total surface, well, as a matter of fact, you'd be able to actually, just by looking at this weak form and with what we already know, you'll be able to solve this problem on your own without actually going on with the nodes. And if you want to, give it a go. Pause the video and see what happens. See if you can work with it, where you assume your U displacement field according to the shape functions. You know how to transform from the x to the psi domain using isoparametric formulation. So there's all those things that are already in place. So you should actually be able to do this without having to look at what's going on in the notes. But for those of you that are not comfortable, feel free to go on. But those of you that want to give it a go, pause this video and see if you can get to the solution yourself. Okay. It's quite rewarding working through that. Okay, so the one aspect again just to remind you of is that the total surface of the body is the union between the parts on the surface where we apply prescribed displacements and parts of the surface where we apply prescribed tractions. Okay, so that makes up the total surface of the body. Okay, so the reason I mentioned this is we shouldn't forget about the zero tractions on the surface. So that they're also just part of your thought process when you work. Okay, but this is just as an overall reminder again about when we look at this, that the whole surface of the whole surface of the structure is given by this SU and ST. Those two things make up the whole entire surface. Okay. The other thing to remind yourself of again is just where we have prescribed displacements, reaction tractions will follow, and where we have prescribed tractions, those parts of the surface we'll just solve for the displacements. Okay. Okay, so we solved the weak form using Galerkin's method, weighted Riddle method. Okay, so that implies the following. Okay, so that when we assume a shape for U, that same form is going to be assumed for the weighting functions. Okay, that is important to understand. So if you go back, because I've put down 1, 2, 3 nodes, the element and its form is now fixed. You saw how we drive the shape functions, but this is now a quadratic element that we are using here. Okay, and so U psi is equal to N1 psi plus Q1 plus N2 psi Q2 plus N3 psi Q3. I'm choosing, so this is a choice I'm making. Okay, it's not something that I could have chosen a linear element, then results would have looked different. Okay, and the linear element I leave to you to do. That's the simpler one to do. I do the more difficult one always in class. Okay, so and V I'm assuming it to be 0 as a function of psi, and W, so this is the displacement in the Y and Z direction to be 0. So this is essentially exactly the same kind of field assumption we made when we did the previous version of the weighted riddle with the polynomial in X, that quadratic polynomial assumption that we assumed. The only difference is here the unknowns that we're solving, Q1, Q2, and Q3, have nice interpretable meaning. Q1 is the displacement at node Q1. Q2 is the displacement at node Q2, Q3 is the displacement at node Q3. If you think back towards that ax squared plus bx plus c polynomial that we assumed, that a doesn't mean the displacement at any point specifically. It's just a full field, and to get the displacement at any point, I have to add up the values of a and b, and of the contributions of the a to the quadratic term, the linear term, and the constant term at any point. And so it's not great for trying to get continuity between elements, as we discussed. Okay, so that's just that. So the weighting function, I'm assuming n1, so the same form, n1, w1, n2, w2, n3, w3, and this is the weighting function for the u displacement. Then there's for the vertical displacement, and the y and the z, I'm assuming to be 0. So you can see that whatever this form is, it's exactly the same form that I'm assuming. Okay, that is important. That's also that's called the Bipnov-Kalerkin method, and this choice, you can verify it for yourself as you go along. You'll see that this choice ensures that our stiffness matrix that we construct is actually symmetric. Okay, you'll see what I mean. The word stiffness matrix is not going to make sense now, but in a couple of minutes it will. Okay, so we have set up, okay, so our function is now essentially set up over -1 domain in psi, and that's always going to be the case. And the reminder for that is we want to make sure our integration is convenient using Gauss quadrature. Okay, so we want to be able to relate this psi domain to the x domain, and that's where the isoparametric formulation comes in. We're going to just say x is a function of psi. That's not a 3, but it's psi. So whenever you see, yeah, so just bear in mind, my 3's and my psi's might look quite similar. I'm realizing it now. Okay, it's n1 psi x1 plus n2 psi x2 plus n3 psi x3, and this allows us to map that. Okay, and because we made a choice that this x3 is slap bang in the middle, because it's 0.5 in the middle of those two things, we know essentially what will happen, as we did look at the special case yesterday, that the relationship is linear, and that the derivative dx dt is going to be a constant. Okay, so dx dt will be essentially 1 over 2. Okay, and you can see that by just taking the derivative here. You'll see that, so it's 1 over 2. But you can do that without worrying, because if you without actually formally taking the derivative, because you know what is the delta in x is 1 and the delta in psi is 2, or the range in psi is 2 and the range of x is 1, and that's where the 1 over 2 comes from. Okay, and then that's it. So you can also always check that things make sense. When you evaluate psi equals to -1n, you get 0. When you get psi equals to 1, you get 1. That's the end of the bar. Psi equals to 0, you get a half. So everything is hunky-dory. Okay, so that's all good and well. Okay, so currently we have now 6 unknowns. Our unknowns are Q1 to Q3 and W1 to W3. Okay, so that's it. But we know that at some point we're going to take derivatives with respect to these things to recover a linear system of equation, algebraic system of equations that we want to solve, because this is the way we package that optimality criterion version of actually the minimum of a sum of the errors squared. Okay, so this is just what the Wattishauser method is all about. So to solve for these, we first have to now look at our equations and plonk these things in there. Okay, so we're going to have to look and say, what do we have? So first off, we look at this term. So when we look at the weak form, and we go through what are the terms that are non-zero and what are the terms that are 0. So essentially, if I look at this first term of the Wattishauser and I go and look at what's going on there, there's like we did in that previous version, you can go and work out the whole thing. But what you'll see is that the only non-zero term is this term here, the sigma xx partial of w u partial x. Okay, so this is the only non-zero term. For the tractions, the only non-zero term is this term. Okay, and the body forces is 0 because there are no body forces in this problem. Okay, so let's look at this first term for now. Now this is our only non-zero term, and we can now go through and say, what does this imply? Well, first off, we need to say what is sigma xx and relate that back to our displacement field. Okay, so we can say sigma xx is E epsilon xx, that's E partial U partial X. Okay, but U is now given as a function of psi. So this partial U partial X, okay, this derivative of U with respect to X, I'll have to get there via psi. So I can say that's partial U partial psi partial X. Okay, so that is now my strain. If I go through the psi worlds first, so take the psi and then I go from the psi world to the X world. Okay, that is first things first. So U is this. If I want to now first just look at this term and say, okay, so let's just take the derivatives of U with respect to psi. This is what I will get. I will get partial n1 psi q1, partial n2 psi q2, partial n3 psi q3. I can write it as a vector, a row vector and a column vector for convenience. Okay, and then that is halfway, and now we just have to have that term, then we have the strain. So we just need to get this d psi dx, partial psi partial x. So let's see, d psi dx, what is that? Well, we have to go and look at the isoparametric form and say that relates x to psi, and then that's the expression that we have because of the midside that shows in the middle, etc. Now I can say that's the derivative of x with respect to psi is just a half. Okay, I can then say dx, well, from this I can see dx is equals to half d psi, but more importantly I can just also relate this back and say, well, d psi dx is then just 2. It's just taking this across this side and dividing by this, you'll get d psi dx is equal to 2. Okay, so this is how it works in 1D. In 2 dimensions, it's a little bit more involved, this getting this dx d psi dx ratio, because it's really just the inverse of the Jacobian. But for now, in the 1D case, things are nice and simple. But this is essentially the Jacobian that we are working with. Okay. Ooh, what happened here? Okay. So now we can write the partial U partial X as du partial U partial psi dx. Okay, so that's essentially that. And what we get out is essentially our description for strain. Okay, so this is epsilon xx, this is a strain in the x direction. What we do is everything that's in front of this q1, q2, q3, we bulk together in the finite element method, and we'll call that our B matrix. In this case, it's a 1/3 matrix. Okay, so that's the B matrix that we have here. Okay, that is important to understand. And so that is what we have. I'm going to finish this page and I'm going to stop the video so it doesn't get too long, and then I'll make a follow-up video on this. Okay, so what we can do is, because we call this B, we can write this more conveniently to say partial U partial X is equal to BQ. Okay, and that is essentially, that is how we can express strain. Okay, and again later on you'll see when we do the higher multidimensional stuff, this B will be such a form that it will give us all the strain components that we require. It will take whatever it needs to get that. Okay, but the bottom line is, this is still the unknowns that I need to solve for. This Q, the vector here, and this B, when I multiply by that, I get the strain out. Beautiful. Okay, so I'm going to stop the video here, and then we'll continue with the second one, just so that the video doesn't get too long and too difficult to download.